So in this lesson, we're going to learn about two different kinds of logic gates, the AND gate as well as the XOR or the exclusive OR gate, and a simple electronic circuit known as the half adder. The lesson will be divided into two parts. The first part is the conventional method, which is the lecture style of method, which we will be doing now. And then the second part will be using Minecraft as a teaching tool to help further understand the topic. So, an introduction. As you probably know, electronics communicate in binary, ones and zeros. So this is at the most fundamental level. This is on a hardware level. So whenever there's electricity passing through the electronic, its state is 1. If there isn't any electricity or if there's no power being supplied to it, then its state is 0. So it's not only electricity. Other examples are like fiber optic, which carries light instead, but it's the same concept. If it is carrying light, its state is 1. If it isn't, then its state is 0. Now an introduction to logic gates. So what logic gates are? Logic gates are just a basic electronic circuit, and what they do is they take one or more inputs and they produce a single output based on the state of the inputs. So we can see, for instance, a simple logic gate, the NOT gate. So it has a single input, which is labeled as A, and then it has one output, which is labeled as C. And we can see that C is the complement of A, or the inverse of A. So if we look at the truth table, we can see that when the state of A is 0, the output is 1. If the state of A is 1, its output is 0. Very simple. So there are also more complicated kinds of logic gates. Over here we can see 8 different kind of logic gates, and they all work differently with their own truth tables. So they take a certain input, and based on the state of their inputs, one or more inputs, they produce a single output. But for this lesson, we're only going to focus on two different kinds of logic gates. The first logic gate is the AND gate, which is pretty simple, as what its name suggests. Only when both of its inputs, only if input A and input B are in a state of 1, only then will its output be 1. Otherwise, its output will be 0. The XOR gate, or the exclusive OR gate, is slightly more complicated, but also, like its English name suggests, exclusive OR, it can either be this or this, right? Like you can only take the car or you can take the bus, right? You can't not take both of them, or you can't take both of them at the same time. You can either take the car or the bus. So for instance, you have A but not B, then you have an output of 1. Or not A but B, then you have an output of 1. You can't take both, you can't take none. Next, we move on to another concept, binary addition. So binary addition, it's pretty similar to the normal addition we do, which is like decimal or base 10 addition. So you have two values. You have an input. You have two inputs. So what happens is, like, for instance here, you take 1, you plus 1. This is binary, so you can't write 2 because this is base 2. So the maximum value you can represent is, well, 1, because you can only show two values, 0 or 1. So 1 plus 1, you're going to get 0, and then you're going to get a carry. You're going to have to move it on to the next one. So these values here are not relevant. This is for the second bit, which we don't know, so we aren't going to focus on that. We're only going to look at single bit addition. So we're only looking at this, we're only looking at this. So when you add them together, they produce a sum. First of all, they produce a sum. So in this case, it's 0. But they will also produce a carry. They may produce a carry. So in this case, they produce a carry of 1, because 1 plus 1, you carry 0, so you have that overflow, so you get a 1. If it wasn't 1 and 1, if it was 0 and 0, or if it was 0 and 1, then it wouldn't produce that carry bit, and it will produce a different sum bit. So here you can see what would happen for binary addition. So if you had 0 and 0, you would have had a sum or a result of 0. Your carry would have been 0. If you had 0 and 1, you would have had a result of 1 and no carry, and the same thing for 1 and 0. And then for 1 and 1, like the example we saw, the result would be 0, but we would have a carry. So now this is the part where it gets interesting. Earlier we took a look at the exclusive OR gate, and we took a look at the AND gate. And when we look at the truth table, we actually realize that it's quite similar to what we were doing in the last slide. It's quite similar to what we were doing for binary addition. So if you look at the truth table, you have 0, 1, 1, 0 based on the different kind of outputs. And for AND gate, you have 0, 0, 0, 1. But if you look at the last slide, we actually see the same thing, where if you do 0 plus 0, you're going to end up with a result of 0. If you do 0 plus 1, you get a result of 1. So this is basically your sum, right? And it's similar to the XOR gate. And if you look at the carry bit, it's actually similar to the AND gate. So what does this mean? There's something that we can do with this, which comes to the next slide, which is a simple electronic circuit known as the half adder, which is done for single bit binary addition. So like we saw just now, the sum is actually the output of your inputs going through an XOR gate. This is your XOR gate. And your carry is actually the output of your inputs going through an AND gate. So you can see in the truth table here, the sum, it goes 0, 1, 1, 0, just like the XOR goes, and the carry is going 0, 0, 0, 1, just like the AND gate goes. So that's it for part 1 for the conventional method. We will move over to part 2, which we will do in Minecraft. So this is part 2 of the lesson, where we're going to go through the logic gates as well as the electronic circuit, the half adder, which we learned in part 1. And we're going to demonstrate how exactly it works using Minecraft as a tool. So first things first, in Minecraft there's this thing called redstone, which is a model of electronic circuitry. And so we're going to focus on 4 different kinds of blocks which are used for redstone, or that we're going to use for this demonstration. So the first one is just called redstone dust, which is basically wire, so it carries a charge. And then you have a redstone torch, which provides like an infinite source of power. So you can see when it lights up, now there's power flowing through the redstone dust. So I can just remove that. There's a lever, and so a lever can be toggled. So when you toggle it, it turns on the power, and you can also turn it back off. And then the last thing we'll be using is a redstone lamp. And all this lamp does is, when it is powered, it turns on. That's all it does. So there are some unique properties which are not so important, but we'll just go through anyway. So when you have a redstone torch attached to a block and you power that block, the torch actually turns off. So this is kind of similar to a NOT gate, you could say. So we can remove that. So this is my input, right? So you can see the lamp is not on. So my input is off, but the output is on. So that's similar to a NOT gate. If you look at the truth table, you'll see how a NOT gate works, and it has an input of 1. When its input is 1, its output will be 0. When its input is 0, its output will be 1. Right? So when I switch on the input, the output changes to 0. So now we'll look at some of the gates which we learned just now. The first one being the AND gate. So you can see the gate that we built in Minecraft, which is not so important to know how it works. You can see it does use that those kind of NOT gate characteristics that we learned earlier on. So, but let's not focus on that. So if we look at the AND gate, we look at the truth table, we know that its output should be 1 when both of its inputs are also 1. So if that doesn't happen, its output is going to be off. So we can try it out now in Minecraft. So I can turn on this lever to turn on input A, and the output doesn't change. But when I turn on input B, now the output turns on, because both my inputs are on. So if I were to turn this one off, it would turn off as well, because I don't have both of my inputs on. If both were off, obviously it would be off. So that's the AND gate. Now the XOR gate, which looks a little bit more complicated, but also we don't really need to know how it works in Minecraft. More so we want to know just how it works based on how we change the inputs, how the output will respond. So if you look at the truth table of the XOR gate, we know that its output should be 1 when both of its inputs are different. When it's either this or that. It cannot be both, it cannot be none. So we can try that. When we turn on input A, the output turns on. Now both the inputs are different. But if I were to turn on input B, now the inputs are the same, the output turns off. When I turn off input A, now only input B is on, the output turns back on. Right? So it follows how the truth table should work. So this is an XOR gate. Now we move on to the half adder, which was the electronic circuit that we built. So what is supposed to happen, this is supposed to represent binary addition, right? So we have over there in the S, we have the sum bit, and then we have the carry bit. So when I do, if we look at the truth table, if we do 0 plus 0, I would have a sum of 0, I would have a carry of 0. If I were to do 1 plus 0, I would have a sum of 1, and I wouldn't have a carry. If I were to do 1 plus 1, then I would have a carry, but no sum. That sum would be 0. So we can see it here in Minecraft, we have input A, we have input B. So if I were to turn on input A, which would be the equivalent of 1 plus 0, on state plus off state, I'm going to get a sum of 1, right? If I were to turn on input B, now I'm doing 1 plus 1, I have a carry, but I have no sum. If I were to do 0 plus 1, I would have a sum, but no carry. So we can see in Minecraft, using these logic gates and building this electronic circuit, we can see how binary addition is performed using these logic gates and how it works together with this electronic circuit.